Okay, hello everyone. Well, we are here for a working session for our physics project, except that right now we are trying to understand physics by understanding metamathematics. And well, that thing on the right there, we're calling it a metamathematical festival, but that's only because it happened to have those bright colors. It is a piece of the knitting together of axiom systems, but I don't think that's what we're going to look at primarily. I think we're going to start off by looking at the analog of theorems on hypergraphs. And so let's see, Nick, what should I be running here? Which versions of what? Is it all in? What's that?
Yeah, two-way rule, and basically it. Yeah, you can just start running the two-way rule replacement notebook with all the functions.
Okay. And do I need to also run Codo1?
You can, yeah, but I haven't changed anything there for the co-substitution. Yeah.
All right. So you claim that you have a version of co-substitution for hypergraphs. So let's remind ourselves what the let me just pull up. Hold on. Let me just make a should that be in the metamathematics section, or should it be? I think we better put it in metamathematics, otherwise we'll just be completely confused. Let's see, what are we at here? We are at metamathematics 45. Let's see if we can actually have a topic where we run over 100. Metamathematics 45 hypergraph co-substitution. All right. So let's remind ourselves. Is there something you can point me to try running here?
Well, I think it would be very descriptive to multi-replace, just a new version of multi-subset replace to understand first, and then we go to the co-substitution version of it.
Okay.
So I have, yeah.
Tell me what to type. So I'm going to apply substitution to a hypergraph. Yes, or what?
Well, hypergraph, it's not specific to the hypergraph. The point is that now you can also basically do substitutions and co-substitution on the subset of your tree, on any subset of the nodes of your tree, right? So that's the overall idea.
So let's do an example. Nick, kind of guide us through an example of doing this.
Well, let's start up maybe with substitution, and we have to remember what. Okay, so when we think about, I mean, if we're doing substitution, we would say something like f of a. Oops, I need to make this much bigger for people. F of a replaced by, with f of x blank goes to g of x. That's substitution. And for which we can do by saying, are we still using substitution lemmas here?
Yes, it's just substitution lemmas has some additional rules for two-way rules and patterns. But
okay, so this, oops, which way around am I supposed to do this? Is it the other way around? Is it the rule first?
No.
What did I do wrong?
In principle, correct. I'm not sure.
Did I do a two-way rule?
Maybe I broke something today. We'll just try multi-subset replace thing. Just the same as substitution lemmas.
Multi-subset.
But without two-way rules. Can you rerun your notebook? Maybe it's
which notebook? The two-way multi-replace?
Yes.
I just did it, so let me try quitting and restarting.
kind of weird. We need to put all these functions into a bucket.
Yes. Okay. There we go. Okay, so what that means is, if I understand correctly, that means the whole expression has the rule applied and it turns it into G of A, right? So now you're going to walk through some more examples here.
Okay.
Yeah, like first thing you should notice that the key now is the list of lists, so it's list of positions. It's basically going forward, it's the list of subsets, so it can contain a list of positions.
Okay, so for example, I say U of F of A, F of B here, then I would just get 1 and 2. What's the first case in which I will get something where there's a sub?
Well, you have to specify it. So it's a special case if your left hand side is a list. So it's a special case it would work as subset replace another.
Okay, so let's try F of X blank, G F of Y blank goes to G of X, Y.
Right.
So why are there? Okay, so hold on. What were you going to say? So those are two different cases with the different bindings of F and G. Is that right?
Yeah. So it says that it did a replacement at position 1 and 2, where when the replacement happened. But there are two ways you can do it.
But I don't understand. If it's done at replacement of position 1, how does it say which one of these from this list? I would have expected it would be a permutation that says which element of this list corresponds to which part number in this expression.
No, that's like, so what it's doing, you have a subset that tells you of two Fs with X and Y. Then it finds two positions where both of them can match.
Yep.
And then you do a replace list there. And you can do it in two ways, because order doesn't matter.
No, I understand, but why is this telling me that this F of X here is matching only at position 1? So if, for example, let's say I did this, and let's say this is F prime. No, that's a bad example. Yes,
No,
F prime.
It's not telling that exactly this, your first F at X is position 1. It can be other way around because it's a subset and order doesn't matter. So you won't have a position 2, 1. You just will have 1, 2.
Try that again. So you're saying these two could match in either order?
Yes.
Okay, so what does the 1 mean again here? Or is it that I should be looking at both of these together?
Well, yeah, both of them. It's a subset of positions. So we have two positions.
I see. This means that the match was at the subset of positions 1, 2. And the order, and since F of X blank and F of Y blank are kind of identical particles, let's call them particles here. All that matters is the subset, because they can match in either order, right?
Yeah, right.
Okay.
And those positions can be like arbitrary positions in an expression. They can even contain themselves. So this can be 1, 1, and just 1.
All right, so let's take a look here. So if I say if I say this, and I say obscurely F of this, oh my gosh. Okay, so that says so this is kind of like a token event graph story, where this event has multiple tokens coming in. So if I'm not mistaken, the multi-subset replace could be, you can make a multi-way graph directly from this. If you don't explicitly show the events as nodes, this would make a multi-way graph. Is that a true statement? I mean, iterating the multi-subset replace.
Maybe. Well, it's very close to the, well, the role subset replace, multi-subset. It's basically the set replace as we have for the physics project, right? The only difference that instead of list of hyperedges, you can have a tree, an arbitrary
Yes, I get
tree.
it. I get it.
And you can do the same thing that you can do with the hypergraphs, but with the arbitrary trees.
Oh, you know what? I was looking for this. Yeah, great. I was looking for how this would work. Right, so this is great. I mean, because I was wondering, so instead of this being, this isn't just it's not a collection of hyperedges, it's an arbitrary expression.
Right.
Right. This is applying a set of rules to subparts of an arbitrary expression. So visually, we could see this as being, in the hypergraph. Yes, this is just going to transform an expression. But now, how do we, let's say for combinators, let's imagine this was a combinator expression.
Mm-hmm.
This would be, normally with combinators, we make a multi-way graph by doing one replacement at a time. But now, is this doing essentially a multi-replacement on combinators?
Oh yeah, it will try all possible.
Right, so
Good
ordinary, so wait a minute, ordinary multi-way combinator evolution does one combinator reduction at a time. But this can do any subset. So let's make a specific example here.
Mm-hmm.
So let's take let us take let's pull up a random combinator thing. Let's see. Multi-way combinator. Let's try and get a multi-way combinator thing. Let's get a non-trivial one. That looks reasonably bushy. Why does that have that in it? That's, oh, I see. It's got that thing that loads that in. That's annoying. Oh, I see. MW combinator graph, which I don't understand why that function isn't provided somewhere else, but anyway, whatever. So that would presumably be, so this is a combinator expression. And then we're saying, just so I understand how this works, I should be able to say, well, if I said multi-subset replace, no, I'm going to need a nest graph of this, I think. And the rules are these ones here. Oh, can I give a list of rules?
Yeah. You don't have to wrap it left-hand side of the list. It will wrap it itself.
Okay. I still trust it more if it's wrapped that way. Okay. So let's give. Why do I have? Oh, because I don't need that. Oh, yes, I do need that. That's that. Okay, why didn't that match? Even though this presumably has a match. Like if I say this, maybe I shouldn't wrap this with the list.
Try at heads arrow true.
This one here, heads arrow true.
Yeah.
Ah, there we go. Okay. So what you're telling me is that if I were to do nest graph of oops. Humph. Maybe it's not doing what we expect.
You should.
Oh, values. I've got to
value.
say values. Yeah. Is values going to be enough? We probably need to say flatten the values.
Yeah. Maybe not. Okay.
Look at this. Beautiful, magnificent.
Right.
So what we're about to see, okay, let's just run it for however long it takes to run. Say 20 steps. Beautiful. There is our combinatorial evaluation using an ordinary multi-way graph. Now, what you are saying is we could actually do 2 at a time evaluation. Is that right?
Right. Hmm?
By saying, for example, in here, instead of just S goes to this, we're also saying, how would this work? I'm not quite understanding how this would work. We're saying we're doing 2.
I'm not sure either what we're trying to do. Because
Well,
you
I
don't have
to understand the relationship between these. Yeah, go ahead.
you don't have a rule of combinators on subsets. It's like, or do you want just to repeat the same rule, the same?
Well, I think if I repeat the same
replacements of
rule,
S's.
it's just combining 2 nodes here, combining 2 edges here. So I think what I want to do is I want to do the minimal case of combinators, of something like combinators, but with disconnected things. So the rules here that I want, let's see, have you worked out what the kind of ruleology minimal rules for your multi-subset replace are? Because what they are is the multi-subset replace.
So this is the same as Wolfram Model rule, because they exactly act on the subsets of hyperedges. So that's the minimal case.
Except it doesn't need to be hyperedges. It could be nested things.
Mm-hmm.
So that's what I want to see. Is I want to see one of these ones where it's nested. So, for example, we could imagine a rule. Okay, what is a minimal case where we can see something which is both nested and you get what I'm saying? I mean, where let's see. In a standard Wolfram model rule, we would have just something where we would say, 1, 2, 2, 3, 2, 4, something like that. That would be our raw material. And then we would say as the rule, something like, well, let's just do that explicitly. Let's just understand that explicitly. So we would say something like, let's pull one up. Trying to find a reasonable example. Okay, like this rule here is one of our famous rules. Okay, so we need to turn that into blanks. And this would be our standard kind of setup. So we would say here, this would be making, so if I just repeated multi-subset replace, so let's say I say multi subset replace of that of let's say 1 1 1 1, and I use this rule.
Maybe you need splice on the right hand side.
Yeah, and I also need something which generates a variable. Yeah. Right?
Like W should be W blank.
Oh, would that work in your setup to have W blank in there?
Oh yeah. To just it's not doing anything fancy. Just gonna insert W blanks.
Okay, but that's not. But how does it end up being unique after that? See what I'm saying?
No, you can always just uniquify it.
Just uniquify it.
Yeah. Okay. Fine. But that's what you mean with the function uniquify?
With the option.
Yeah. No, there's no option. No.
There's no option.
For this one, I don't think so.
I just use a module.
Yeah. Option is just for more fancier functions like substitution lemmas.
Okay, so here, what do I want to do? This has an extra level of list here, right? Why is that?
It's always a list of something because there could be multiple outcomes. So we have a list of hypergraphs.
But these hypergraphs are trivial. These aren't hypergraphs. Wait a minute. This doesn't seem right because this should be a list of hypergraphs, but this isn't. These aren't hypergraphs. They're singletons.
Oh, that's what happened. I guess. Well, it in this particular case, what happened?
Maybe I gave the wrong input here. Are we sure splice will do the right thing?
Or just what I usually, for some examples that I run today, it usually requires splice here. I guess.
Humph. Well, okay. Maybe. Do you have some examples you could show, or you could send me?
Well, without splice, what would it do?
That doesn't look bad. That's produced 2 hypergraphs.
Yeah.
So then what we would do here is, again, we could use nest graph of, let's see, values here. I think it's just values, if I'm not mistaken.
Just you have to be careful because when you just have X blank, it can actually match something more than just atom. It can match a hyperage itself or something like that.
I see.
Very weird things.
Right. Okay, well, let's say slash semi length of X equals 0. Is that useful? Just have it match just the
So just the atoms as integers, then you can say integer.
No, but they're not always integers because they might be W blah, blah, blah. I mean, they are probably atom Q. Yeah, so we can just, yeah, we should just say question mark atom Q.
This pattern is atom.
Say that again?
I'm not sure that that pattern is an atom Q. It's not. Because it's like a list of simple name and a blank.
But I don't think we need it to be a pattern, do we? Or do we? Oh, we do need it to be a pattern. Right, we do need it to be a pattern. Right, it does need to be a pattern, otherwise it's not going to work. Is that true? No, for these purposes, it does not need to be a pattern. Right, because this is not an accumulative rule.
Oh yeah, if you just have an usual multi-way.
Right, and then we can do an accumulative one.
The question there, not the condition. Pattern test.
Okay, so nest graph starting with, I might get confused by all these lists here, but let's hope not. Let's say 2, 3. What's happening here? This seems wrong. What's it doing? Maybe we need to go. What the heck is that? Well, let's just go 2 steps.
Wait, where is your function? But nest graph accepts function. Right?
Yeah, that's really stupid. Yes. So, oh yeah, what am I doing here? I'm just doing totally the wrong thing. That's the hash. And that's the ampersand there. And let's get rid of the, well. Okay, why is this doing that? So let's say vertex list of that. Oh my gosh, what is this? So I think it's getting one too many levels of lists in it.
Oh yeah. If you just say values, it's going to be, maybe you need to concatenate after that.
Maybe. I think this died after that. I don't think this is quite right. But I think it doesn't help that we've got so many lists lying around. Maybe we should not use lists here. Maybe we should make a hyperedge be called, you know, not a hyperedge. Maybe we should make a collection be called the C. See here, that would still help. That would still work for you, right?
Yeah.
And then
your rule left-hand side. Okay.
So what? Yeah, okay. So you're saying that should be a C there.
No. The outer should be just a list of subsets. Maybe you also come up with a head for the hyperedge itself.
Okay, all right, okay.
But there is no list at all.
Yeah, okay, let's do that. Let's have these be hyperedges. And well, I mean, let's just say.
And on the left-hand side too.
I know.
And you don't need atom. Yes.
Right. Well, let's leave it for now. Okay, so here, this becomes a hyperedge. And this becomes a collection.
No. Leave the list. It says that there is a subset of hyperedges.
Oh, okay, fine. Okay. And then this here, well, let me write it out explicitly, is a collection of two hyperedges, right?
Yeah.
Do I need the catenate now?
Oh, it's gonna be, yeah, you need one.
This didn't work. Now look, we've got C of C there. That's not what we want. How do we stop that?
I think.
I don't think we want to see here. I think this wants to be a list. Because it's splicing it into, it's those two hyperedges. This collection will be spliced in. Can this be a list in your formalism or not?
For sure. Right hand side should be. And then maybe you need to splice it.
Okay, I'm
No,
confused.
no,
I don't
sure.
think splice isn't going to do anything. I don't know whether that helped. No, it's wrong. Okay, let's try this again. Okay, let's try to understand what this is doing. So from within, I don't think we should use C. I think we should use lists. Because I think this actually is a list. Okay, what is it doing? So it's taking from every, and you say we don't need the atom queue, fine. It's taking from every hyperedge, which is a pair of things there. It's taking a pair of hyperedges and it's converting those into 4 hyperedges, correct?
Yeah. But it's replacing it at the first hyperedge it's found. So if you put list there, it kind of should be a splice. Because this list of hyperedges on the right hand side is going to be inserted to the place where the first match will happen.
Okay. Why do we get this? Why do we get these? Why do we get individual hyperedges there?
Maybe it's better to understand it first just by single application, not an S graph, and see at positions. See what happens at positions. Maybe there's like outer position matched against the whole hypergraph or whatever. This is a very confusing concept. And you haven't even got to the co-substitution yet.
Right. Okay. Okay. So what is happening here? So this is matched at positions 1, 2 in H1, H1, 1. So for example, if I put an H1, 1, H1, 2 here, this will match in 3 ways. That's what I would expect. Okay, so now let's understand the right-hand sides. I don't understand them at all.
Without splicing. Splicing makes it more confusing.
Okay.
So the right-hand side should be a list of something. So just pick a first element.
But that first element has a sublist in it, which we don't want.
Yes.
And that's where we want the splice, because we want to splice this into the outer thing.
Yes.
Okay, that looks mildly promising. So let's try then this nest graph. And we don't need the catenate, do we? Oh, we might do from the after we deal with the values.
Yes.
What the heck happened here? So this
Wait, nest graph expects the output to be a list, right?
Yes.
Of things.
Yes.
And we have a list of hyper. Yeah, catenate should be there. Seems like
After the values thing. Okay, so let's look at this. This is a function applied to this list here, this inner list here. Okay, so now let's look at values of that. Okay, why are there sublists there?
well, first element is should be a list of hypergraphs, right?
I wonder what would happen if we said flatten /at, just for fun. I doubt this is right. So if we said flatten to this values here, no, flatten /at that values. That seems to me to be a correct single collection of hyperedges. Do you agree? No, I don't understand why these are still left in there.
Just a single collection of hyperedges. Shouldn't be so many in one.
Well, there should be 4. Yeah, you're right. Okay, let's try this again. Okay, you're the expert on this, so help us out here. So we've got a collection. Our structure at all stages is a list of hyperedges.
Yes.
Right. So here we've got a list of hyperedges here. So what we want to get out of this is a list of lists of hyperedges, correct?
Sure.
Where each element of that list of lists of hyperedges, the complete thing is the multi-way output of all possible results from the original from replacing the original hypergraph. So in particular, if we say, let's just see what we want. Resource system, resource function of multi-way system of, I think this is the right way to do it, Wolfram Model arrow, and then let's see, we want something like this. then we want to say the hypergraph list 1, 1, list 1, 1. We want to say, let's say 2 steps. Oh, why didn't that work? Do we need to say resource function? What the heck? Why didn't that work? Okay, multi-way system documentation. Arg. Oh, I know what the problem is. You have to do Wolfram Model arrow, and then a list of those lists. There we go. Okay, this exceptionally confusing object is, we're going to map. I'm not trying to be obscure here. Oh my gosh, what did I mean there? I meant map framed. I'm really not trying to be obscure, but that's what you understand what I'm doing there, right?
Mm-hmm.
So those are the pieces that we're trying to get out.
Mm-hmm. Yeah.
Okay. So now let's go back up here and see what we got. Because what we got here still had the H11s in it. We hadn't removed the input here. Do you see what I'm saying?
Right. Well, not, but why we haven't removed it?
I don't know.
Right.
You tell me. I mean, maybe that's how multi-subset replace works.
No, it works like subset replace. So like when you just use a subset replace on a list and match a subset, it will destroy all the elements of the subset and just put the result.
Okay,
let's
be very straightforward here. Let's take this here and let's just say f of x, y, z. Okay, that's what we expect, right? X, y, and z are all bound to 1.
Right.
Okay, so here, let's get rid of the splice for a second. Okay, so what do we expect here? What's that?
Splice is doing something weird. There's no splice for a given head, right?
No, there isn't. So what we're doing here, maybe we want to catenate instead. What we're doing here is we've got, this is the correct thing. This is a, well, actually, what's really strange here is that this claims there's only one independent hypergraph here, and this says there are 2, but they're actually isomorphic.
Right.
Up to variable renaming.
Yep.
So that's a different, separate issue. But now here, I think if we took values of this, okay, now we take, okay, so the first thing we want to do is get rid of, I think we want a level 2 catenate of this thing. Because we want to get rid of the first level. We don't care about that. We're going to combine. Wait a minute. Values is going to have one level of wrapping for where the pattern replacements took place. And then within each pattern replacement, it can have multiple things here. So we want to catenate those first 2 levels. Okay, so now we've got,
so
why do we have an,
Well, what would help if you, instead of splice, just apply any symbol and see where it get applied. Right.
In here.
Yeah.
So just put an F in there.
So that it would be clear what's happening.
Yeah, okay. So that's what it's doing.
And for
So
some
in
reason,
fact, what we want to do, go ahead.
yeah, for some reason, if F splice, then it's weird. Maybe if you then replace F with the splice after that.
No, we
The
don't
whole
want it to be
substitution
spliced. We want to just flatten everything. We want to take this, flatten all the results.
No, you need the splice here, exactly splice.
Why?
I think.
Oh,
Well,
we
if you
can't
have
tell here. Yeah, okay.
if you have
Okay.
3 hyper edges as initial condition, you'll see why.
Yes, I do see why. Okay, let's try making that be spliced. What
It's
the
not
heck?
splicing correct. It's some kind of bug right now. Let's try just F and then replace it with a splice. I don't know what's happening. I'll look at it later.
Okay, all right, okay, fine. Okay, so then there's an F there, and then what do? Then we do
Replace F with the splice.
right now.
Yeah. It's not gonna work inside the association. I think.
Okay, so then I have to do this, and then I'm saying values of this. And then I'm replacing that with F with splice there. Okay, but then there needs to be one more level of catenate, doesn't there?
Yeah.
Okay, so your claim is that this should be that. Let's call it F hack. And then let's say values of this / F hack goes to splice, and then we catenate that.
You need an arrowhead.
Okay, all right, dandy. Okay, so now we say in here, wherever it was, where did I have my nest graph? Did I get rid of it? Oh, well. Okay, so then I want this. And I want to say nest graph of this thing with this as a hash. And then I want to apply that to make my analogy down here, H11, H11, maybe another one of those. Okay, now the one problem is, I think this is probably correct, but there is a problem that we're not canonicalizing. And that's why we're not seeing mergers.
Yep.
Nick, how can we canonicalize in this situation?
Well, we have a function. Just if this W were a pattern, unique one, then it would be just canonicalized patterns function after you catenate.
It is a unique pattern. After, okay.
It is unique, but within each hypergraph, it should be canonicalized, right? You look at the hypergraph and you just replace all the same W's.
Yeah, right. So what should it be called here? That's
just map canonicalized pattern function. That with the lowercase.
Okay.
That looks very promising. Okay, now that is to be compared with this thing here.
Is it the same?
Oh, for goodness frigging sake. We do not need 100 computers to do this. Why is it even doing that? I hate to even imagine why it's doing that, but well, hopefully these computers were useful for something else. Come on, wake up, computers. Da 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 da. You know, anyway, I won't even make analogies between different kinds of technology, stages of technology, and what kind of ridiculous things. Okay, interesting. Not quite the same. This one has 4 branches. This one has 3. Okay. So what we want to do here.
Wait, how do we explain the difference?
Well, I don't know. I mean, why don't we just run for 2 steps and see what
compare the vertices.
Let's just run for 1 step and compare the vertices first. Now it's just going to be a single vertex. Let's run for 2 steps. Okay. Well, here. Oh, that's not what I wanted. Great, bit incomprehensible. Okay, all right, so let's look up here. Okay, what I'm going to do is I'm going to put my little framed trick over these. Oh, that's the vertex list. Just need to map framed over it. Oops.
Yeah.
Okay. Someone on a live stream is asking, how come quantum computers help with the graph theory? The graph theory we're implementing is many layers below quantum mechanics. So it's
Wait,
from
they both
this.
have 5 elements. Oh, okay. I'm not looking at the correct. They turn variables into numbers.
That third box. Yeah, right, correct.
That's not 2, 3.
Yeah, exactly.
There's 2, 2, 3s here. And
Right.
here there's a
1,
3,
yeah,
1,
exactly.
3.
Right.
But we're not describing, no, these could be in any order.
Oh, okay, let's try and find a match there. Oh, is it the
4's there.
Is it the last one? Is it the last box that matches on the bottom? Yeah.
Yeah, but wait a second. These aren't. Are these sorted? They're not sorted. That's why it's not canonicalizing the same way. These are sorting the hyperedges. This is not sorting the hyperedges. Is it?
No sorting is going on.
Okay, so what we need to do then
Sort it. Yeah.
In addition to this, after canonicalized patterns, we need to sort, do we not?
Yeah. Sort at star. Oh no.
Oh, is that the same or is that different again? Oh, look,
What's
look,
3?
no, it's similar. It
Wait.
might even be this. No, it's not the same because that's
Wait.
got 2
Why?
merges. Well, that's got 2 merges, and this has only got 1 merge.
Where? Wait. Can you go down?
Yeah. 1 merge.
I only see. Oh yeah. Oh dear. Dread. So close.
Okay. Look, let's zoom out for a minute because we haven't even got to. We didn't even get.
Substitution, yeah, I know.
We're not even close to co-substitution. Okay, let me try to understand here. So first point is, what you're doing is defining a way to replace tokens. So let's try to define what you're doing. So this is replacing tokens wherever they appear. Right? Not necessarily in a set. Correct. So those tokens could appear inside an arbitrary tree structure.
Yeah.
Now notice that the thing that they appear in is not necessarily orderless. Right, which is, I suspect, why we're having trouble with this canonicalization.
I do treat the order of this each subset kind of special. So if I find tokens that match your subset, then I do it in all possible orders, basically. Right.
Right, but you put them back into the structure in the order in which they came from the structure. So in other words, the structure itself does not sort them.
Correct. Yeah.
The container of tokens is not immediately sorting. But so you're making a replacement. Let's see, whenever you can replace, okay, replacing sets of tokens wherever they appear, not necessarily in a container that is a set. So in particular, I could perfectly well have I could have a tree. So in other words,
You can show it with subset replace easily. Because it's not sorting the list. List is not a set.
yeah, I get it. This phenomenon. But what I was saying is you could say, okay, so if I have a tree, some random combinatory type thing. So let's say a random tree of 50 elements. Okay, so here's my tree. So you're saying that I could go in and I could replace this subtree, and my pattern could combine that subtree with this subtree here.
Yeah.
Right?
And even this tree with its children.
Yes, right. So this tree, it could be this tree and this tree are both getting replaced. Very weird operation.
They're not both getting replaced. Only the first one's getting replaced. And others is just dropped. If you match a subset of.
Well, but these are being ingested. These are being bound for the pattern variables.
Yeah.
This thing, there'll be, so for example, in the naive case where we said, for example, where the replacement was a full tree and a subtree goes to something which is, the list of X and Y, then I would get 2 copies of the subtree, right? One in the X binding and one in the Y binding, right?
Yeah.
Okay.
Yeah. So this let's see, you can't get that in the standard subset replace. About that for a second.
Yeah, well, did you like mention some multiplicity, like one subtree matched against it pair patterns, like with itself? I think that can happen here.
Subtree. Two different patterns can match the same subtree. That's token multiplicity. That's having automatic token multiplicity, I think.
Yeah, I don't have multiplicity of this kind.
But you do allow the same.
Yet another generalization. Yeah.
So the same subtree could match different patterns. In one match, the same subtree could be providing the binding for two different patterns. Right? So this is in a single match, the same subtree but that's not what you have right now. Is that correct?
Yeah, you should think of it like I have subsets of positions. So you have different positions in a tree, and I consider all the subsets of length that I provide on the left-hand side of my loop.
Yeah, I get it. Right. Okay, so how does this help us understand? Okay, so we had talked about can you give a demo of co-substitution for hypergraphs just so we know where we're going here?
I just wrote it today, so I have one.
What's that?
I wrote it just this evening, so I'm not sure. I don't have a good example. I have one.
Okay. Do you want it? You could send me the. Okay.
Yeah, I sent one. Which is weird.
I know I'm not going to understand this. Okay, what the heck is this? Okay, X a pattern, Y a pattern. I see. Oh my gosh. You know, co-substitution is one of the more head-spinning concepts I've seen.
Nick, can you narrate this? Can you walk us through it?
Oh, my head is spinning too.
Well, that's not encouraging.
Writing its implementation is much easier than understand what it's actually doing.
Well, that's the story of Ruleology in general.
Yes,
right. The rules are
exactly.
simple, the behavior is not. Okay, but all right. Well, we should understand this, but let's segue to a different topic because I think we're not. But the main thing you've done here is something that I had wanted to do, which is you've defined the obvious generalization. Let's see. So I had thought about. We've got tagged hyperedges, and we've also got a container that is not just a set. And you're defining how we can do essentially multi-substitution. Yeah, with both tagged analogs of hyperedges and or tagged relations, we could call them, embedded in arbitrary symbolic structures. Right. So in a sense, what you're doing is general idea is replacements for tagged relations in general symbolic structures. Well, for sets of tagged relations in general symbolic structures. So this is the generalization. So pattern matching. Okay, so ordinary pattern matching is the one-to-one version of this. With each replacement actually not even relations, tagged sub-expressions. Well, it's just for sub-expressions. Yeah, this is what it is.
Okay.
And I'm going to parenthesize the English sentence so we know how to parse it. I'm surprised one doesn't do that more often. There should be some version of parentheses, which is a markup for English sentences. What version should we use? We can use angle brackets to indicate parsing. Gosh, why does one not have that?
Well, we could start.
Yeah. That's so strange that that's never been a punctuation mark in English. Okay, in any case, replacements for sets of expressions. So ordinary pattern matching is the one-to-one version with each replacement replacing a single sub-expression. So this is more like the general token event graph version, where you can take multiple sub-expressions. And the only question is, where do you put them? Where do you put the result? So you've grabbed two subtrees, right? Where do you put the result?
Well, right now I put it at the first match. It's because I was mimicking the subset replace behavior. But in general, yeah, I can, if I require, for example, so my right-hand side also be a list, I can splice it in the corresponding positions, right? If I have return the multiple results.
Right, well, so basically one's taking, okay, so step one, pick out certain sub-expressions. Leaving stubs where they go, right? Now the question is, okay, step two, take the sub-expressions and generate a new list of sub-expressions, possibly of different length. Okay, now we have to reinsert them back into the original expression. Step three, some kind of reinsertion. Okay, this is where token event graphs are good because they don't reinsert.
Right.
So token event graphs don't have to reinsert. But when there is reinsertion, causal dependence is more non-trivial. Because there are spectators. And the spectator parts of the expression have to be carried, represent causal relationships. Because they're connecting an old expression to a new one because it has the same spectators. If that makes sense?
Yeah. In a sense. Not completely.
Well, so what I'm claiming is, okay, so the first point is that you allow both space-like separation of subexpressions and tree-like separation of subexpressions here. You're not allowing branch-like separation of subexpressions. In step 2, you could in principle have branch-like combinations of subexpressions. But you're not including that.
Yeah.
So hold on. So what we're saying here, what we're learning is that as we try and have more arbitrary structure for the containers of the things that are being matched, it is more difficult to know how to heal those things after the replacement has been made. It's less obvious. If the thing is just a big bucket of hyperedges, you take some away, you add some in, it's all good. But if the thing that is the container is itself a thing with great structure, it's much less obvious how you put the new thing back into the old thing.
Yeah. Right. But I don't think we should ever consider anything besides just trees.
Yeah. Well, the question is there a generalization? Is it, because I was looking for something that is the general multi-computation function. And this seems like it's very close to being it. The most trivial multi-computation function is just nest graph, in which there are multiple outcomes from every input. But here, let's see, instead of just having a function that applies to a whole input, you're saying how to go in with sub-expressions. So this is a big generalization of replace list, I think.
Yeah, that's what my original description of the multi-replace function was, as a replace list on drugs.
Okay, fair enough. So that's why you called it multi-replace. Okay, so
yeah.
Multi-replace, what are you calling it?
Oh, it's going to be a multi-replace. Right now, I called it multi-subset replace, but it behaves as my multi-replace that's already in the repository. But I want to update it because the only thing that's changed is the special case when your left-hand side is a list. If you don't have a list, then it's the same.
Okay. All right, let's change topics here, because I think this is this was going to be just the aside, but it's been a long aside. Okay, the thing that I wanted to look at.
Quantum proof?
Yes, I want to look at quantum proofs. Do we already have a notebook for quantum proofs? Let's see here.
I don't necessarily recall that we had one.
Yes, we do, 35.
Oh yeah, right. Oh my gosh,
Okay,
we've had so many notebooks.
Yeah, I know. Well, let's set the stage for this. Okay.
Right.
So what we're trying to do is we're trying to understand when there are multiple paths.
Yes, right.
By which something can be proved. What can we say about the homotopy? What can we say about the deformability of those paths into each other? Okay. Mm-hmm. And maybe we need some more examples. So this is a particular example. Let's try, well here, let's just try a longer run of the same thing. Let's try this, and then let's get, let's say 10 steps. And then let's say, all right, let's try, oh look, AAA seems to not occur very, very quickly. So let's take a look at AAA, the 10 steps, and let's see what that does. Okay, so what this is showing is those are all the paths it claims for getting to AAA.
Right.
Let's just try, it's just to fill it in. Let's just try making those all red. Okay. So those are all possible paths to reach AAA.
That's right. Yeah. And there are some
Yeah.
holes. Well, there
There's
might
some
be.
small
We
holes.
can't necessarily tell. Might need to
Well,
look at it in 3D. Oh yeah, I forgot about this flatland problem.
well, we can clearly help by doing
Oh. Okay.
let's do 3 and 3 here.
See, it
It doesn't seem to have a lot of holes.
that's the point. It actually doesn't seem to be a hole. That's interesting. This is
It's
a
an
nice
unholy graph, so to speak, with a W. Okay. All right. So how could we measure that it doesn't have any holes? What would be the graph theoretic characterization of having a hole? Also, this is a very special case here. Let's try some other cases where we have let me see. So we need another. Let me look at what we've got here. I think we've got some cases of graphs that are at least somewhat more complicated. Now, these are ones with long causal invariance paths, which might be related. Yeah, I would think this rule that branch pair to this common successor. This may be too computationally expensive, but this is going to be, okay, this will just show us the intersection between the forward and past light cones. I was afraid of that. Let's try 6. No, doesn't find that vertex. Let's try 7.
Oh,
There we go. Okay, let's do graph 3D. And hidden somewhere inside that weird protein is, okay, hold on. So what we're looking at here is evolution. So that's a proof. That's
that
all
thing.
possible proofs.
Let's take a look at that. Different angle.
Well,
Okay.
it's very compact. I mean,
Yeah.
if we take the subgraph, how do we
Uh,
get the subgraph? We need the subgraph that's all those red things.
that might not even have hole. Well,
I don't think it has holes. I don't think this has holes. But let's get that subgraph out. So that subgraph is the union of those path graphs, I think. So essentially what that is the subgraph is, we've got a highlight graph here. So I claim that is the graph union. Does graph union take a list?
I don't think so.
No, I think not.
No.
Right, no.
Just a sequence.
Okay. That's like union. Okay, there's the subgraph. And we can say, let's label the vertices. Okay, so this represents all possible proofs of that result. And as we can see, that the proofs are very compact there. Right, there is no hole in those proofs. So let's check our original thing up here and see if there's a hole. Just check that we don't find a hole in this one either. So that's this thing here. And that's like 10 steps there. And this is BA goes to AAA. Okay, there's our non-holy collection of proofs. So right now we have found no holes in the, so this is the complete set of proofs, and we can imagine a proof-to-proof transformation inside here. That,
yeah.
okay, what's going to cause there to be holes? When in doubt, as they say in the releological business, ruleate, and just let's just try all the cases. Okay, so let's see how we would do this. So what we want to do, yeah, given that we might as well start from the initial state. Go ahead. Yes.
I think we need to find a way, a proof that's like that was done with two different rules. Like that would be easier. Maybe just do it artificially. Like come up with two rules that you can apply one of them multiple times to make a result, and apply the second one to come up with the same result, right?
Yeah, I think it's going to be hard, but let's try it. I mean, the most obvious thing to try to do is something like saying something like, let's say AB, where A goes to CC, B goes to DD, And then we have a fix-up rule at the end that says CCCC goes to, what's that? I was thinking goes to A, but maybe I'm wrong about that.
I was thinking you will have both C and D, and then they go to something else.
I see. So that the CDDD like this goes to E, for example. Okay, so let's take a look at what that does. No, that's not going to do anything, right? Because CC is not going to do anything. We need this to have, it needs to be a little bit of a stem cell kind of effect like this, right? So it extrudes things, right? So what that's going to do, if we look at the states graph for that, that's going to have we're never going to have CCCC. If we do that, I hate constructing these things. I just hate it. There we go. There's our little squiggleroo down at the bottom there. Right. So if I do the states graph structure, and I do it to like 12 steps, right, it'll get a little tangle at the bottom. Right, there's the tangling associated with that thing. Okay, so now let's say, and let's get okay, let's say ACEBDB. AEB is a good one. Okay, so let's try to get this thing AB to AEB. Oh, come on. It's a no hole type situation. Look, so how's this working? So this is going down one side. Oh, I see. It keeps on deciding. It can either add to the B's or add to the A's. It's not locked apart. Could we lock them apart? I think we could do it with regular expressions. I'm not sure we can do it with local string rules. Okay, so the question on the table is, are there cases in which the subgraph that goes to a particular outcome, I mean, there clearly are cases where that can happen. I mean, for example,
Sure.
You know, there's this one, he still has it on his website. Let's find out. Unless he has revised. There we go, he still has it. Oh wow, it's all been improved. Christopher has a better version of this on his website.
Yeah,
but
I've
anyway.
heard this from traffic, right?
Right. So this thing is a very definite, it's got holes.
Oh yeah.
So how can that, and I think, and that is a multi-way graph.
Mm-hmm.
So in a sense, this is an example of where you have non-trivial homotopy in the multi-way graph.
Yeah, non-trivial topology, right? I mean, we can always just look at multi-way graphs that have holes in them, and then pick out proofs that we know are going to that are going to be interdeformable.
Yeah, I know. But what multi-way graphs have holes in them?
Well, what about like the black hole examples that you've shown? Well, but then
Those
they
are
never,
plausible
but
graphs.
they're never confluent.
Yeah.
So that's not right. So there needs to be a hole, but it can't just ramify, never to become confluent again, right?
Okay, so what leads, I think I thought about this at some point. What leads to these holes? And what is the significance of these holes? I wonder if Christopher, by any chance, has actually written that down. I think this is quite old, but yeah, so it's clear that there are solutions to this game that are, wait a minute, didn't I have a thing? I was looking at this. Yeah, you know what? I forgot what I was looking at. I was looking at something which might be relevant to this. Let's take a look. Well, I'm not sure that these will be. This is multi-way graphs for aggregation systems. Those are branch hill graphs. These are distinctly not topologically non-trivial. Okay, let's take a look here. Game multi-way systems. I was starting to look at this. Maybe I had it in a different place. Oh, here we go. This is the Towers of Hanoi puzzle. What is this now? So this was an attempt at the multi-way graph for Towers of Hanoi. Or the game. This is the set of game moves, which is the multi-way graph for this game. Okay. So notice the presence of a very big hole.
Mm-hmm.
Okay, that was Christopher's version of this. Maybe I have a different version. Maybe he sent me this on the grounds that I was incapable of figuring out how to do it. Let's take a look here. What's this? This might have been from Ed. Let me see if there's a. This was 2020. Let's just take a look whether we actually have stored things from 2020 about this. How do you search within this single directory? This is always absolutely stupid. Oh. Well, maybe that's the right place. Multi-way game. Okay, let's see whether that's right. Oh yeah, look at that. Lots of multi-way game things. I forgot I did these. Okay.
Definitely check these out. Oh.
Tic-tac-toe.
Wow.
Yeah, this was a bulletin I was going to write and didn't get around to yet. So that's the multi-way graph of tic-tac-toe, which I believe has no holes.
This is interesting.
that would seem to be a very mandala-like no-hole situation. Okay, let's go backwards here, see whether there were things earlier. That's Nim.
Yeah.
Toads and frogs. Sure. I guess I should write this bulletin as well. Yet another thing to do. Obviously, I had figured out some amount of stuff here. Oh, this was completions, where you're conflating different states of the game. Towers of Hanoi. Well, there we've got it. I mean, we've got to get from 111 to 311.
You have to go around. Yeah.
Okay, can we make a version of this? Oh, look at that.
Nice. Very interesting. Now, this says something about irreducibility, right? The fact that you have to take this circuitous route.
Possibly. That's why Towers of Hanoi is an interesting game, sort of. But what is the significance of this, though? So we've got two different proof paths. Two different ways of essentially showing that the initial state is equivalent to this final state here. I bet we can do an analogous thing with strings. Is it obvious how to do that? Actually, let me copy this multi-way game code 05. Okay. And where did he have this? Oh, it says the following is not correct. Somehow the largest disk rather than the smallest seems to be moving. So maybe this was never quite, maybe we have to untangle this a little bit. Let's see what this looks like here. I have no idea why this has light green. Let's at least have. I have no idea. I'm going to pick colors. I'm going to pick purple and orange, just so we can see it more easily. Why is this taking so long? What is it doing? Okay. All right, what's happening here? So what are those circles? Oh, those circles are the graph nodes.
Yeah, right.
Which we should remove. Nick probably knows how to remove those. It's just some kind of place at center, right?
Sorry, I wasn't paying attention. I was making this simple string replace.
Oh, you've solved the problem. Okay, all right. Okay, let's look at this. Just a second. Okay. I mean, we've got, okay. So can we embellish this and see its whole get?
Widened or?
Yeah. I mean, I want to see the thing. So your basic claim is if we add to this just sort of random A goes to AA,
I see.
AA goes to A, for example, that will embellish, but it will still
Right.
have holes.
Right.
So let's take an example here of what will be a proof that would be. Let's see what we have up here. So we want a proof here. This system with initial state CBA and you're saying, well, even CBA goes to ABC. Right. They're not totally convincing holes. Because what we really want to see is a bunch of stuff in between where the webbing, where.
Yeah, right.
Is that right? I mean, is that what we want to see? Is it what we want to see?
You want there to be vertices, say between CBA and ABC, like in the middle there, right?
But maybe there can't be. Maybe there can't be. If there are vertices, that's not what we're seeing in Towers of Hanoi, for example.
Right. Yeah. Yeah.
Can we make this bigger? Can we make the hole bigger in an easy way? Or is it in fact the case that okay, what's happening in this case? This is basically okay, this is a case where there is confluence.
Yes.
I.e., there is confluence, but it takes a while. Okay, so the basic claim is
Well, there's what is there? Destructive interference, right?
That's
This is
the
an
claim.
example. Yeah.
That's the claim.
Oh, did I ruin the punchline?
Well, I don't know whether that's the punchline. I mean, I think we've got examples. Okay, in terms of things that are hard to prove causal invariance, what do I talk about here? Okay, so I did a big search here, needless to say, for cases where there is a branching and then there's a merging again. And this takes 10 steps in this case. So this page basically has okay, so what is the significance? All right, so let's take a look at one of these. Let's say, well, this is the size of the minimal objects where they converge. So let's take one that's a little bit modest, the 4 here. Oh, for goodness sake. Okay, A goes to AA, this one here, right? And then we're going to prove, yes, that's what we want to do. So we want to say, in our original thing here, always convenient when we've already studied the same thing. 4. This one here. Then we want to say, starting with A, let's say starting with A and eventually winding up with that big ba 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 thing. And we want to go, let's say, 4 steps. No, that didn't work. 5 steps. There it is.
Do I see a hole?
Well, I don't know whether we have a hole. Let's find out if we have a hole.
We have to go 3D?
No, I think we just want to do the hole finder. We want to have the thing that just generates this. Well, yes, there's a hole.
Can you scroll down?
Yeah. Yeah,
Bingo.
there's a hole. Yeah, there's a hole.
Pretty significant one.
Yeah.
Okay.
So let me just.
Oh, great. We can find them. Now we can start to
Now, what is
study
the
what they are. Yeah, right, exactly.
Right. What do they mean? I mean, so this is 2 paths to a proof. Where there's a lot of there's a lot of different stuff that's happening on the 2 sides. Let's just for fun, let's see if we can get an even bigger one. I mean, so this one, yeah, this is a perfectly decent one. But let me just, for the hell of it, let's just see. That one looks rather fun. Oops, we're the 12-step one, where we're just going from A to B in 12 steps. That may be just a counter of some kind. I see, we might as well start with AA to B here. Actually, we might as well start with that there. Help. What did we do wrong here?
Nick.
What did we do wrong? A goes to AA. Let's start with A here. Something stupid has happened. Okay, so there's our graph. And now, okay, so now let's do this. What the heck? Wait a minute, I must have gotten this wrong. AA goes to B. It's just a single direct path there. So what the heck are we talking about here?
Well, that's why I was surprised that it would take so many steps.
Oh, it can go to AAA. Oh, this is a sort of degenerate case. Never mind. This is kind of a stupid degenerate case. Yeah, you see that it can go through one easy path and one long, hard path. Okay, so this is a case. Maybe this case here. Well, let's see. Are there any cases where it looks really juicy? Hey, B goes to B. Those are all easy. That one looks like it. Oh, look, that one says it needs 2,698 things. So let's look at the 14 case. Okay, so this needs these, but then we're going to think about the interpretation of these things. I'm just trying to get more data here. I'm not sure this is the optimal way to find holes, but this is, I mean, in a sense, a critical pair, the non-convergence of a critical pair represents a hole, I believe. Right, that's a way to characterize a hole, which I believe has a relationship to the sort of homotopy type story.
Well, sure. Though our framework's somewhat different. And especially as we begin to think about observer theory, the Roolead, these other features that they don't have in HOTT. These holes might attain a different.
I know, but let's just understand what would their holes. Okay, let's look at this case that we have here. We might be able to find other cases, but this is saying a hole can be removed by a critical pair lemma by knitting it together with critical pair lemmas.
I mean, in HOTT, it means you just can't identify those different proofs. That's what it means, right? Those two proofs aren't equal, and so you can't introduce a higher homotopy that deforms between the two of them.
Well, you could by knitting it together with completions, right?
But if you had one, well, yeah, but then if you have one, then you have one, right? If you are able to translate between the two proofs, then you're able to compute that. So you've constructed it, so it's available. And then
okay, but I mean, clearly we can add a completion to this, which is, you know, AA goes to B, AAB.
Well, sure.
And now there's no hole.
Are you sure?
Well, there is a hole. There's a little bit of a hole.
Yeah, still in. So it depends on. I mean, if you wanted to treat this, it's reductive. But if you want to treat this as a toy model for an observer's reference frame, if you introduce, well, see, how do these relate to the entailment fabrics and the festivals that we were considering before? In terms of you admit a number of axioms to your reference frame, and then you take the confluence of those entailment cones. So if you introduce perhaps more axioms, say the right axioms, you can knit over the patches or the
Well, the point
holes
is, it's
in
not a
there.
cone. It's a cone with a hole in it. Because this thing is supposed to be an entailment cone, but actually it's got two different pieces to it. It's an
Yeah.
entailment cone.
Right. That's why I call it a fabric, because you have two different, it's not just because you have multiple axioms here, do you not?
Yeah, we do. But the
So
thing that I'm
you have
confused by,
you have multiple entailment cones, then you have the fabric, but the fabric is has holes in it. For the top,
no, but
both
the
of them
fabric
do.
is going to be a space-like thing. It's going to be a thing across here. So what's going to happen is there's going to be, here's what it is. There's two different regions of metamathematical space that both lead you to this result, but they are themselves disjoint.
Mm-hmm.
Okay, so I'm keen to just see a slightly bigger example. Frustrated this one didn't work. A goes to AB. Okay, BBB. I don't quite understand. Maybe we just start it with that BBBB thing. How big is it going to get? Help. Well, it didn't fail yet. But let's just try 14. Maybe that's enough. Okay, in any case, the basic point is, okay, the basic claim is, different disjoint regions of metamathematical space lead to the same result, i.e., what does it mean that they're
The question is, can an observer admit something like this into their reference frame?
or can they emit both parts of it?
Yeah, even though they're disjoint. Because you can imagine in the Roolead that there's this kind of topology. What about within an actual observer's reference frame?
Yeah. Well, so the question is whether an observer who has ingested certain mathematical theorems what this is basically saying is that there are disjoint sets of mathematical theorems that lead to the same results. And the question is, so what? Alternatively said, there are disjoint axiom systems that lead to the same theorems, which is sort of interesting. So that's like reverse mathematics.
Yeah. I mean, aren't they just entailment cones?
Which?
There are different entailment cones that contain the same theorem
in
them. And then when you take their fabric, the fabric is not completely connected.
Yeah, that's
fabric
right.
has holes in it.
Yeah, that's right.
Right. But this is how we've been characterizing observer reference frames as of late. And the question is, what's the significance of there being some sort of genus in entailment fabric in an observer's reference frame?
Right. It means that, I think it means there's these disjoint areas of mathematics that can both lead to the same results, but those areas of mathematics are not In other words, the question is, can you map those areas of mathematics continuously to each other? Or do they merely lead to, in other words, let's say that you're trying to.
Right. Well, that's the thing is you could continue to admit more axioms, further axioms, basically their entailment cones into the fabric. But as we've discussed before, for instance, if you just took some explosive cone, right, like A two-way rule B or X two-way rule Y, you could probably use that to piece together your different entailment cones if there are holes in the fabric, right?
Yes,
but
everything.
But I would not advise that an observer
you will
do
conclude
that.
Right,
Yeah.
false will imply everything.
Right, so it's a kind of Pyrrhic victory, right? Where you deal with the hole in your fabric, but you've shredded yourself as an observer, so to speak.
Right.
So there might be certain cases. This is the thing. These are the kind of the trade-off questions. There might be cases where there are holes in the entailment fabric, and they can only be patched together by entailment cones that shred the observer. And in that case, there's no way to resolve the holes in the fabric. There might be other cases in which they can be resolved, but you have to admit further entailment cones into the fabric. And so long as they're non-shredding, then it can be done. And
right. Well, so this is basically, can you hold two different points of view, two different axiom systems, and not just be confused about everything?
Yeah.
Right. I mean, that's the basic question: is can you, if you admit the axioms from the different sides of the well, essentially of metamathematical space, different sides of the whole in metamathematical space, then I wonder what this is doing. Then let's see. Then will this lead to an explosion? In other words, we know it will lead to a particular theorem. We know it leads to a particular theorem being established. But will it lead to an explosion of other theorems?
And so the question is, for instance, so suppose, for instance, that you have some well-established axioms in your fabric. So you have the entailment cones of those in your fabric, but there's still some genus, and you want to resolve.
Right. You want to add a completion.
You want to have deformability in your entailment fabric. So suppose it occurs to you that you could admit a given entailment cone, a new one, and so there are a couple of questions. One is, well, will it shred you? Is it the kind of thing that you would really want to assign falsity to it, and you probably want to avoid putting that into the fabric? That's one question. The other question is, do you understand those axioms? Because what if, for instance, you find some nice, basically a rule, the entailment cone of that rule actually does make your fabric smoothly deformable, but you have no idea what those axioms are kind of paramathematical. This is an instance in which paramathematics.
Okay, that's an interesting case. Yeah, that's an interesting case.
You're basically having alien outsourcing.
Right. Is the bridging axiom paramathematical? And that's basically the bridging axiom would be the bizarre new idea in mathematics, so to speak, that bridges these two different areas. You know, that's essentially that's what we're talking about there, essentially.
Yeah.
That and the question is it the case? So what this is basically suggesting is that there can indeed be non-trivial it's not obvious that, okay, there can be radically different proofs of the same proposition. And the bridging of those proofs, showing the equivalence between those proofs, could, if you add an axiom to show the equivalence between those proofs, or to make those proofs smoothly deformable, you could wind up adding an axiom that basically causes you to be able to conclude false includes everything.
Well, that's one outcome, right? One outcome is it could shred you as a mathematical observer, but the other outcome is it works in a kind of, functionalist way, but you really have no idea what you've just done. You don't really understand the axioms.
Yeah, right. But that's right. But although that's but in a sense, this is like an unsolved problem. And I mean, to see this particular thing, to see this is not a typical kind of thing people do in math. That is, this would be, to see two different proofs of the same thing. When you see two different proofs of the same thing, it's basically showing you a math problem. How do you get from one to the other? Let's talk about this in the case of game graphs. Okay, I'm sure that there are cases where we already know that for towers of Hanoi. There are cases where you can get to the same outcome by very different paths.
Yes.
And where there is no smooth deformation from one path to the other.
Okay.
Now, what's the significance of that? You've made a commitment to go on one path. What is the significance of that?
Well, you mean for gaming?
Well, I don't know. I'm trying to understand it. Okay, what we have imagined.
Well,
okay, so the analogy in mathematics is the introduction of false, or if you do a completion, it will lead you to falsity, so to speak, is presumably the analog of destructive interference in quantum mechanics.
That's what
very bizarre connection.
That's what we've conjectured. Yeah,
right.
For some time now.
Yeah, I know. That's a truly bizarre connection.
Wow. It fits right in.
Yes. Well,
one thing in gaming that I've thought about before is it depends on what the kind of game it is. You could imagine if you have a game that's played in parallel between two players, and there's some element of trust that's required. You have player one and player two. Player one happens to go down one side of the graph.
Yeah.
Player two goes down the other side. If there's destructive interference, then somewhere in the middle, player one, like let's say player one
will not trust player two because it looks
player
like they're
one,
doing crazy
right?
things.
Exactly. This is
Good
kind
idea.
of the game theory aspect to this, especially if they can see what the other one's doing, and they can have confidence in their own strategy, but they don't have access to the graph in terms of information. And there's going to be distrust between the two players. On the other hand, if you had some gadget that could translate between the two of them, like a contract or something that could, or something, some sort of service, then they could know, oh, this other person's taking this other route, and it seems as though that route is going to work, something like that.
Well, that's an interesting analogy. I mean, so then the idea is two cooperating players go down disjoint paths.
Mm-hmm.
So they don't understand each other's strategies.
That's right.
And therefore, sort of, it's hard for them to cooperate if they don't understand each other's strategies or something. Yeah. Whereas if they do understand each other's strategies, they can kind of back each other up. But if they've gone down disjoint paths, I mean, if the paths are continuously deformable, then they can kind of back each other up.
Yeah, and you could introduce some other constraints, like let's say they're they're deformable. Like if it's a complicated topology, maybe you can translate from one to the other, but it just takes a long time, in terms of computation. And then players could have some bounded computation available to them, and they have to decide whether or not it's worth trying to figure out what the other player is doing or not. And these kind of microeconomic.
Well, that's interesting. I mean, that is a very interesting way to look at these things where there are, like, imagine there are two Towers of Hanoi players.
Right.
Okay.
There you go. Yeah.
And they are solving the puzzle in the same kind of way. Then they can each they can each leverage. If two Towers of Hanoi players are solving the puzzle the same way, they can look at each other's micro recursions and see, they can learn from each other's micro recursions.
Imagine you have two players, they're both asked to solve Tower of Hanoi, and there's a certain payoff that they're both given if they both solve, the problem successfully, right? And then there's a certain payoff that they get, like if they defect because they don't think the other player is going to win or not, for instance. And maybe the payoff's greater if they both happen to solve it together, but they're not going to want to take that strategy if they're not convinced that the other player will successfully solve it. And if there's non-trivial topology in the ludic multi-computation that they're doing, then they might not trust each other and they might defect and not cooperate.
Right. I don't think you have to go full game theory on it. I mean, I think the basic question is, can these two players, can they learn from each other, from what each other is doing? If they have a certain amount of computation that allows them to go, to do, because it's a bunch of micro recursions on each side. You try this, you see whether that works. You try this, you see whether that works. If they've gone on completely different paths, looking at each other's micro recursions is not going to help, because they're just in some completely different part of the space.
Yep.
Whereas, so thinking about that in terms of mathematicians, what this is saying is, if there are two different proof paths, then two disjoint proof paths, then what it's saying is, it's basically saying the mathematician who's over doing algebra or doing, I don't know what, in the Langland's program or something, one radically different kind of thing from another, if they're off doing their different things, it doesn't really help them. Progress in arithmetic number theory over here doesn't immediately help progress in some kind of category theory thing over here, because there isn't a continuous deformation from one to the other. They might both be able to prove the same theorem, but there's no continuous way to get from one to the other.
Right. They'll only know if they both happen to submit similar conference paper at the end or something, right?
Yes.
And then then the theorem's named after both of them, which is actually something that happens quite often.
Right. But okay. But so then what's the significance? Is there a broader significance in to the existence of such things? For example, I mean, what's probably the case, I mean, this is the analog of quantum mechanics in metamathematics. This is basically saying, when is it the case that there isn't immediate agreement? Yes, this is the point. This is the same thing with this game case. There's not immediate agreement about an objective reality of metamathematics. That's the point. These two, I mean, if you go down different sides of the whole, there will not be agreement about objective reality of metamathematics. That is, you won't have the same view of what's there in mathematics, of the ontology of what's there. You'll have disjoint views of that. Mm-hmm. Just like in quantum mechanics, this is saying there isn't a definite classical path. There isn't the same classical path. It's a thing where there are apparently disjoint paths that take a while to converge.
And in economics, it could be the case that even if there is a law of one price, you could still have price volatility or something being under or overvalued.
Well, there's also arbitrage, right? I mean, this is the arbitrage opportunity of quantum mechanics, so to speak. Because this is the thing where two prices have, where you're saying where at an intermediate stage, eventually the thing will converge.
Yes.
But so then what's Planck's constant in mathematics? Or, well, what it is actually related to the maximum entanglement speed. Yeah, which and what, for example, there's sort of a question of what areas of mathematics have fewer holes in them versus more. We should wrap up because not least I've got to go give a
talk
talk
on metamathematics.
Well, mathematics. I think more on mathematics than metamathematics. Although now I've been infected by metamathematics, so I'll end up talking about that. All right. Well, we had some questions on the live stream here about this question about hyperruliads. Are hyperruliads capable of emulating a computational ruliad? If so, is there still an event horizon between the emulated ruliad and the rest of the hyperruliad?
All right. This
is a good question.
These are great questions. Yeah.
If emulation is possible, is it distinguish between the hyperruliad's emulation of the ruliad and the computational ruliad itself? That's a good issue of whether, if you look from the hyperruliad, I think the answer is the ruliad will look like a black hole to the hyperruliad. That is, just like to us, a decidable thing, like at the center of a black hole where time stops, will look like that just burnt out. I'm pretty sure that what it will look like to the hyperruliad, the ruliad will look like a thing that burnt out.
So so you're saying the ruliad, if you're in the hyperruliad, the ruliad's basically hyper-decidable, something like that. Yes.
Yeah, well, it's decidable with respect to the whole. The ruliad is not decidable, but the relative to the oracle. Yes, this is the point. In the hyperruliad,
yeah,
the ruliad goes to all this trouble to figure out what it's going to do. And the hyperruliad just says, forget it. In one step, I can tell you the answer is 42.
That's what I mean when I say hyper-decidable.
Yes.
Yes, it's decidable.
Right, just like in the center of a
computation. Yeah.
Right, just like at the center of a black hole, you can say, you can do everything you want gyrating around in your spacecraft, but I know the answer is going to be that you're going to be, time is going to stop and you're going to be splattered at this space-time singularity in the center of the black hole. I think that's the story. And we don't understand as much as we should about hyperruliads and the transfinite hierarchy of hyperruliads and so on. And possibly, the speculation is, although we're now developing slightly different speculation about the continuum hypothesis, but the speculation might be, if you commit yourself to living in the ruliad and not the hyperruliad, then it is, in a sense, that that implies something about the continuum hypothesis. But in particular, this is my latest claim, is that the only contingent fact about the universe is that we live in the ruliad and not the hyperruliad. The only sort of fundamental contingent fact. There's additional things which are specific to observers, but I guess it's only one part, because eventually you're going to have to say much more about the observer. So it isn't really right to just say that's the only contingent fact.
Well, but that's what they all have in common at the bare minimum.
Yes, that's right. All possible observers. Well, actually, all observers with whom we can communicate. So the hyper aliens.
You mean the hyper observers? Yeah, for whom we're in a black hole, right?
Yes, for whom they say, poor people in that universe that just corresponds to the Rulliad, they just ended up at the center of a black hole. It's all very boring there. I do like the concept of a hyper alien, though. That's a new concept. The I mean, the hyper aliens. That's kind of the in the sort of I suppose in the simulation theory of the world, the hyper aliens are looking down on our universe, our Rulliad, and saying, look, that one is 42. So I suppose from that point of view, that's a sort of an interesting view. Actually, I hadn't thought of this before.
What, that we're like a grade school problem.
Yes.
For some hyper observer, right? This is like something that you just learn us wrote, basically.
Yes, right,
Yes.
exactly. Except that they might say, with respect to the hyperrulliad, there's this black hole. Effectively, time has stopped for us relative to them because their time is infinitely faster than ours. Their time is actually, that's an interesting question. I mean, their time is transfinitely faster than ours in some way. See, this is where things get complicated because I don't really understand the relationship between. Yeah, this was the paper that Alan Turing wrote when he was a graduate student. The one called Systems of, what was it called? Systems of Logic Based on Ordinals or something. You know this paper? This is his most incomprehensible paper,
right,
that he wrote when he was working with Church, which is an attempt, which is basically the story of oracles and hierarchies of oracles. And I don't know the relationship between the transfinite, I don't really understand the relationship of transfinite numbers to computation. And that's what we'd have to understand to really know how, this is an amusing thought that it's an amusing thought irrelevant to us because yes, it could be the case that the hyper aliens are, playing with us like basic arithmetic, so to speak. But since we have no access to them, it's like, well, that could be the case. That it's some, and in some, I suppose, in some sense, it's, I mean, in the hyper panpsychism idea, where.
Yeah, I mean, keep going.
Well, right. I mean, principle of computational equivalence tells us that there is, computation throughout the universe, so to speak, which is kind of and if you then choose to say that computation is like sort of whatever the thing that is like computation, which I think is not quite correct. That's doing it's. Computation is more than consciousness, so to speak. But in the view that it's just that consciousness is the same as computation, then that's sort of panpsychism. And then hyperpanpsychism would be this idea that throughout, that there are essentially consciousnesses throughout the hyperrulliad, so to speak. And that therefore it is inevitable, if in that model, it's then inevitable that there exist consciousnesses who are playing arithmetic with us, so to speak. I mean, in that theory, by the way, it's sort of inevitable that there's, they're the alien observers throughout our universe too. Anyway, I think
so. Time cake. I think hopefully that resolves the question, but we haven't really delved into the hyperrulliad.
Wait a minute. What is Nick sending about hyperalien?
This is the ending of Men in Black.
Oh, the thing with the thing with the marbles, Nick.
Yeah.
Oh, it's they don't call them hyperaliens, do they? Although
no, it's just something that happened at the end of the. I was thinking about that too.
Yes, it's a very nice sequence.
I remember that. Yes, I remember that.
I mean, it's but they're
We're all
They're
thinking
still
about
thinking
it.
about it in physical space, so that's a pretty junior case relative. And I think it exceeds the power of a mere the question of CGI and the
Hollywood
Hyperrulian.
producer, yeah, right.
Right. Well, no. I'm thinking, imagining CGI, even CGI and branchial space is an interesting thing to think about. Let alone, in other words, that's a kind of an amusing question. Is what is the Anyway, let's not get into that. We'll right. Well, this was very interesting and good progress. And I think, Nick, by the way, that a little side thing at the beginning, I think is really worthwhile for understanding sort of how we generalize hypergraph rewriting for arbitrary expressions, which is something I've been curious about. But they're clearly, it's a bunch of weird hair there. All right, and we're still running here. Let's see whether I wonder if I should leave my computer running or whether that's a formula for disaster. I'll come back and my computer will be. That's what happened a few days ago. We were running some stuff and it went totally out of control, and even my very big fine computer with lots and lots of cores crashed miserably with some. I think, yeah. All right. Well, good. Thanks, guys. Thanks to folks on the live stream, and see you.